Foundational principles of heat exchangers. Okay, so heat exchangers are pretty much the workhorses of chemical processing. And, every single design decision, it's this constant balancing act. You've got your technical performance on one side, and then you have to think about cost, size, and weight on the other, especially for something like aerospace, right? First up, let's talk performance. The number one metric here is the overall heat transfer coefficient, or what we just call U. Think of it like a grade for your equipment. It tells you how easily heat is flowing. It basically combines all the resistance you get from the fluids and even the wall of the exchanger itself. And what's really crucial to get is that U is almost always limited by the slowest part of the process. Like trying to transfer heat into the air versus a liquid. That's a huge difference. Okay, second takeaway. To get the U we want, we mainly use three types of equipment. There's the really simple double pipe setup, which is great for smaller flows. Then for big, industrial-scale jobs, you've got the shell and tube exchanger. This one's smart. It uses these internal walls called baffles to make the fluid move across the tubes to really maximize that heat transfer. And finally, there's the cross-flow exchanger. You'll see this a lot in things like air conditioning. And finally, we've got to get real. We have to talk about something called the fouling factor. See, in the real world, you get buildup, deposits, corrosion, you name it, on the surfaces, and that messes with your efficiency. Big time. This fouling is a huge deal. Just to give you an idea, deposits from something like seawater can slash your heat transfer coefficient by almost 30%. So yeah, we absolutely have to account for it when we do our calculations. Mastering these core elements, performance coefficients, equipment types, and real-world degradation is essential for any chemical engineer. Let's dive into more detail.
In the world of chemical engineering, there's this one single number that pretty much governs the design of everything, from a car radiator to a massive power plant. Today, we're going to break down that number, and I'm going to show you why it is the key to efficient heat transfer. It really all boils down to this one fundamental question. Every single heat exchanger you've ever laid eyes on is an attempt to answer this exact challenge. Whether you're trying to keep an engine from overheating or generate electricity, the goal is always the same: move that heat as efficiently as you possibly can. So here's our roadmap for today. We're going to start with the big one, the overall U value. Then we'll get our hands dirty and dissect a heat exchanger to see how we even calculate that value. After that, we'll use it to find the performance bottleneck, account for that real-world gunk factor, and finally, we'll take a peek inside the engineer's toolbox of common designs. Okay, let's dive right into our first section and meet the hero of our story, the overall heat transfer coefficient, which everyone just calls U. The best way to think of U is like a performance score for your entire system. A really high U value? That means you're moving heat like a champ. A low U value? Well, that means something is slowing you down, creating a bottleneck. This one number conveniently wraps up all the complex physics of heat moving through solids and fluids into a single, useful value. And here is why U is so incredibly important. This elegant little formula right here, it dictates every heat exchanger design, period. If you know how much heat you need to transfer, which is Q, and you know your temperature difference, U is the magic number that tells you exactly how big your heat exchanger area, A, needs to be. It's the linchpin of the entire design. So the big question is, where does this powerful U value even come from? Well, to figure that out, we've got to look inside a heat exchanger and see what's actually fighting against the flow of heat. So let's build this formula piece by piece. We're going to use the most classic, simple example there is, a double pipe heat exchanger. Just picture it. You've got hot fluid flowing through that center pipe and a colder fluid flowing in the space around it. Heat naturally wants to move from hot to cold, but it's not a free ride. It has to overcome a few obstacles to get there. Think of it like an obstacle course for the heat. First, it has to get through that sluggish, slow-moving layer of fluid right up against the inside wall. That's your inside film resistance. Then, hurdle number 2, it has to conduct its way through the solid metal of the pipe wall itself. And finally, it has to push through another one of those slow-moving films on the outside to reach the second fluid. That's the outside film resistance. Every single step adds resistance. Okay, now let's turn that obstacle course into math. Don't let it intimidate you. It's actually pretty straightforward. Since U is a measure of how well heat flows, or its inductance, it's simply 1 over the total resistance, and that denominator is just the sum of our 3 hurdles. Let's break it down.
That first term, 1 over HI, is resistance from that inside fluid film, and we just scale it by the ratio of the areas. The middle term is the resistance of the pipe wall itself. That depends on the pipe's outer and inner radii, RO and RI, its length, L, and its thermal conductivity, K. And that last term, 1 over HO, is the resistance from the outside fluid film. You just add them up, take the inverse, and bingo, you've got your U value.
Now, theory is one thing, but let's see where this formula really shows its power. We're going to look at 2 case studies to see how a real engineer uses this math to find the weakest link in the chain, what we call the controlling resistance. All right, here's our setup. We've got hot water flowing through a standard steel pipe. In case 1, we just leave that pipe out in the cool air. In case 2, we take that exact same pipe with the same hot water, but this time we expose it to 100 degrees Celsius steam. The only thing we are changing is the fluid on the outside. Let's see what this does to our resistances.
Whoa, okay, the results for case 1 are pretty staggering. The inside resistance from the water, tiny. The resistance of the steel pipe, practically nothing. But look at the outside resistance from the air. It's absolutely enormous in comparison. What this is screaming at us is that the air on the outside is the bottleneck. It's over 200 times more resistant to heat flow than the water side. So, as an engineer, this tells you that spending any time or money trying to improve the heat transfer on the inside of the pipe would be a total waste. The air is your entire problem.
But now, watch what happens when we swap the air for steam. The inside and the pipe resistances, they're exactly the same, of course. But look at what happened to the outside resistance. It has absolutely cratered, from over 0.6 all the way down to practically 0. It is now the smallest resistance of the 3, by a long shot.
And this chart just shows the reversals so perfectly. The bottleneck has completely flipped from the outside to the inside. Now that water side resistance, RIP, is almost 20 times bigger than the steam side resistance. It's a total role reversal.
So why such a dramatic change? Well, it's because when steam condenses into liquid water, it releases a massive amount of energy. That makes it an incredibly efficient way to transfer heat. So if you were the engineer on this project, you'd now ignore the outside completely and focus all your attention on improving heat transfer inside the pipe. All right, let's keep going, because, in the real world, things get messy. Heat exchangers don't stay perfectly clean and shiny forever. Over time, a layer of deposits, or scale, or even rust, basically gunk, builds up on the heat transfer surfaces. And this gunk acts like a layer of insulation, creating yet another resistance to heat flow that we have to plan for. And this is what we call the fouling factor. And of course, not all gunk is created equal. As you can see from this table, thick, viscous fluids like fuel oil cause a lot more problems. They have a much higher fouling factor than something like clean steam. As an engineer, your job is to anticipate this and build it into your design right from the start. And please, don't underestimate these numbers just because they look tiny. In one of the examples from the source material, a fouling factor of just 0.0002, that's it, from seawater, caused a massive 28% drop in the overall U value. Fouling is not a minor detail. It can absolutely cripple your entire system. So now that you've got a solid grip on the physics behind the U value, let's just take a quick look at the actual equipment where engineers like you apply this knowledge every single day. While there are tons of designs out there, the core principles are always the same. We've already analyzed the simple double pipe. The shell and tube is really the workhorse of the chemical industry. You pass one fluid through a whole bundle of tubes while another flows around them in a big shell. And then you have cross-flow exchangers, like your car's radiator, that pass a gas, like air, over a series of tubes. In every single one of these, the goal is to calculate and optimize that all-important U value. And that, right there, is the ultimate takeaway. Calculating the overall heat transfer coefficient doesn't just give you a number. It gives you a roadmap. It tells you exactly where the biggest problem is, where the bottleneck is in your system. And that's where you, as the engineer, need to focus your energy to create a better, smarter, more efficient design.